Tim Klein, Christopher Søholm, and Sebastian Tørholm. And my name is Ulrik. So, what is Kleenex? Kleenex is a programming language for streaming processing of data. Programs are given as context-free grammars with unrestricted ambiguity and unbounded look-ahead. We do, however, restrict the grammars to be non-self-embedding, which I will get back to in a moment. So grammars can contain embedded semantic actions, which can be arbitrary code. But in this talk, I will focus on simple printing actions, which print output strings to the output stream. The implementation is a compiler that fully disambiguates the input grammar at compile time, and the compiled programs execute in linear time with streaming I/O. So this is an example of a Kleenex program. It inserts 1,000 separators in the form of commas in numbers occurring in a data file, and leaves the rest of the data in the file intact. The blue identifiers here are non-terminals, with main being the designated starting point. The green parts are regular expressions, which have the semantics that they print the matched parts of the output. And the quoted red strings are semantic actions that consume no input symbols, but have the side effect of printing the quoted string to the output. So what is not shown here are the other semantic actions of Kleenex, which include effects for manipulation and printing of string variables. So this program is ambiguous, since the non-transformation accepts any sequence of digit symbols and inserts 1,000 separators, whereas the other part of this top-level alternative called ID is a transformation that accepts any sequence of symbols, including digits, and just leaves them alone. So how does this actually execute? So starting from the main non-terminal, we apply the rules of the grammar to derive a sequence of terminal symbols, which is an interleaving of input symbols and semantic action symbols. A derivation is matching if the subsequence of input symbols matches the input given to the program. And for a matching derivation, we execute the corresponding subsequence of action symbols. So if a grammar is ambiguous, there may be more than one such derivation, and the semantics dictate that we must choose what is found by a backtracking parse, also called the greedy leftmost disambiguation strategy. Okay, so the programs execute in a streaming fashion, which means that output can be generated before all of the input string has been seen. So for example, this program, when seeing any sequence of non-digit symbols, will immediately output them to the output stream. As soon as it sees the beginning of a number, it will start to buffer its input, since the position of the commas that need to be inserted depend on the length of a whole number, which at this point is still not known. So as soon as a non-digit symbol is seen, in this case a space symbol, the rewritten number is written to the output stream together with a space symbol, and the program then again proceeds to echo any non-digit to the output. We say that such a streaming behavior is optimal if the output symbols are generated as soon as they can semantically be determined from the input string. And this example is actually an example of something that's not fully optimal, since any insertion of 1,000 separators in a number that begins with this prefix here must have 1 as the first digit. So to be optimal, we should actually output that 1 symbol here. The next symbol might be a comma, depending on the length of the numeral, but at this point we still know that a 1 must be written. So the algorithm that we have designed for evaluating these programs in a streaming fashion are optimally streaming for so-called cover-free programs, which I will get back to in a minute what it means. It uses constant amortized time to process each input symbol, and constant space if the grammar has a finite look-ahead property, meaning that all ambiguities can be resolved by looking a bounded number of symbols ahead in the input stream. The implementation determinizes this algorithm into a deterministic machine called a streaming string transducer, which was recently introduced by Ulrik and colleagues. And the compiled programs, by compiling these machines, operate around a gigabit per second on a single core. So let me go through the compilation steps of Kleenex. So starting from a Kleenex program P, we translate it into a finite state transducer TP, which is a non-deterministic transducer with the property that any computation path corresponds to a derivation of the grammar. These machines can be decomposed into two machines, an oracle and an action machine. The oracle is a non-deterministic transducer which maps each input string to a set of codes, where each code uniquely identifies a path in this machine T. The action machine is a deterministic machine which in a streaming fashion can translate such a code into the corresponding sequence of action symbols. The oracle machine can then be disambiguated and determinized to obtain a deterministic machine, which also in a streaming fashion translates each input into at most one code. And these two deterministic machines are then compiled via C into programs that can be executed in parallel, with the output of the oracle program piped into the action program to obtain this streaming behavior. For the translation from programs to transducers to terminate, we require that the input grammar is non-self-embedding, which is a syntactic check on the grammar that essentially ensures that the input language is regular. And by doing this, we also avoid the inherent lower bound complexity for context-free parsing, which is M of n, where that is a complexity of multiplying n times n matrices. Okay, so let me go through the computational model that we use in the compilation. So a transducer over input and output alphabets sigma and gamma is a finite automaton extended with outputs on transitions. We also allow to use epsilon symbols in the input and output labels, which indicates the empty word. We furthermore restrict the transducers that we use such that the only kind of local non-determinism that can occur is in special choice states, in this case state 1 and 2. And those states must have exactly two outgoing transitions with indexed epsilon symbols that indicate the priority of a non-deterministic choice. So a backtracking search will always prefer trying the 0 choice before the 1 choice. A successful path in a machine like that is any pairwise compatible sequence of transitions that begins in the initial state 1 and ends in the final state 6. The existence of such a path can also be written like that, where we contract the input and output labels into sequences. And we use a fat arrow like this to indicate the same thing, but where we ignore the epsilon symbols. So this is a non-deterministic machine, since it can also map two input A's into two B's by, so in the first case we follow this path once, but we can also go this way around twice to translate both occurrences of A's into B's, and then finally non-deterministically go to the final state and accept. And the set of all the paths denote a relational semantics between input-output strings for the transducer. So we can easily decompose such machines into these oracle and action machines I talked about. And we do that, to obtain the oracle, denoted by an uppercase C here, we replace all of the output symbols in the machine. At choice states, we output a bit which indicates which a non-deterministic choice was taken, and all other output symbols are simply erased. For action machines, we read a bit in choice states to guide which way to go, which eliminates all of the non-determinism, and we erase all other input symbols. So it can be shown that the relational semantics of a transducer now equals the composition of a relation denoted by the oracle and the partial function denoted by the action machine. To define agreed leftmost semantics for oracles, we introduce the notion of minimal paths, where we say that a path between two states P and Q is minimal if the output of the path, which is a code, is the lexicographically minimal code of all outputs that read the same input string. And such a path is unique for any choice of P and Q and input string U. So if we define the agreed oracle semantics by only considering the minimal paths by uniqueness, this is a partial function, and we get a partial function semantics for transducers, which are the greedy semantics that we want to compute. So we can do this in a streaming fashion by evaluating the oracle transducer in a streaming fashion with the greedy semantics. And in order to do that, we define the notion of a path tree, which is a representation of the set of all minimal paths that start in the initial state and read some prefix of the input seen so far called U. And such a set can be drawn as a tree as follows, where we draw shared prefixes of paths by introducing branches in the trees, and we order the tree in lexicographic order, such that this is the least path, and this is the next one in the order. Oh, sorry. Such a path tree has a stem, which is what we name the path from the root down to the first branch in the tree. And the stem is intuitively the longest common prefix of all paths that read an extension of the input seen so far, in this case an A. So at this point, when you have seen an A, we can safely output the 0 symbol here, since any path that successfully reads an extension will also output that symbol, and thus obtain this streaming output behavior. We can incrementally compute a path tree for a string from a path tree of a prefix of a string in the following way. So starting from the first path tree, we process each leaf in lexicographical order. Starting from a leaf, we apply a depth first search to build a new path tree from the given state. And as we go along, we mark the states that we visit. If at some point we visit a state that we have been in an earlier iteration, we know that we have already visited that via a lexicographically smaller path. And in that case, we stop the search and we prune the current branch up to the closest branch in the path tree. We also prune all branches that lead to states that have no outgoing transitions with the next input symbol. So doing this, at some point we will prune, or at some point we may prune a path up to the topmost branch in the path tree, which will lead to the stem being extended. And in that case, more output symbols may become available for output. In this particular case, it is actually sound to prune the path leading down to state 4, since the language accepted from state 4 is completely contained in the language accepted from state 5. And we say that 4 is covered by 5. So the notion of cover-free that I talked about in the beginning of the talk is that a Kleenex program is cover-free exactly if this situation never occurs. And in that case, it turns out that this approach will give the optimal streaming behavior that we want. And it should be noted that since checking for this property precludes checking regular language containment, this check is p-space complete to do. So to recap, the simulation algorithm successively computes path trees for longer and longer prefixes of the input, and in each step it checks to see if the stem of the path tree has been longer, and in that case it outputs the new parts of the longer extension of the output. The path of, the set of all the accessible path trees that we can generate in this way is not finite in general. So if we want to determinize oracles taking the path trees as states, that is not going to work in general. We can, however, find some finite structure in this set and still get a deterministic machine. To do that, we need to reduce path trees to their essence. And we observe that this streaming algorithm doesn't really need the internal states and the input symbols on a transition, so those we can forget. And furthermore, all branch-free paths can just be contracted by removing intermediate states or nodes and concatenating the labels on the paths. And what we obtain is what we call a reduced path tree. Such a reduced path tree can be seen as being comprised of two parts. One is a static part called a abstract reduced tree, which is obtained by forgetting, furthermore, the labels on edges. And the set of all such trees is finite now, since it's bounded by the number of ordered full binary trees with k leaves, where k is the number of states in the transducer. By naming each edge using a position-based naming scheme, where notably the stem will always get the same name, r epsilon, we can see that the reduced path tree here is fully determined by the static part together with a dynamic part, which is a valuation of bit strings to each name in the static tree. The incremental path tree computation can be applied to these abstract trees as well. And what do we get if we do that? Well, we can read an A and compute the extension, and then we can reduce the result. And intuitively, this will describe how to go from any tree of this shape with any labeling of edges to an extended tree which will have this shape. And the edges in this tree will be labeled by a combination of edge names and the bits on the new transitions that we added in the extension. So this can be turned into an update that describes how to also go from a evaluation of a tree of this shape into evaluation of a tree of this shape. By iterating this process until we have saturation, we can construct a deterministic register machine whose states are identified by these abstract trees. When we are done, we can just forget about the structure of the states and just enumerate them and let that tree structure be implicit in the current program point. And this representation of machines can then be rather straightforward, be compiled into or translated into a C code, which is quite efficient. Okay, so let me quickly talk about the performance of this. We apply a few optimizations to the results of this determinization, and all these are orthogonal to the underlying principles. The most important one is maybe constant propagation and liveness analysis, which takes something of the previous form and actually can reduce it into something like this. We also apply a finite look-ahead in the SST representation to reduce the state space, and symbolic representation to just keep the size down of the representation of practical programs. And finally, we have implemented a form of deforestation to fuse these Oracle and action machines to get rid of the intermediate codes. So this is a benchmark of the first program I showed in the beginning of the talk. And all the blue bars are just different configurations of Kleenex with optimizations turned on and off, and with GCC and Clang for compilation. So the fastest configurations operate around 1 gigabit per second. And we have compared this to two implementations of the same program in Perl and Python using standard built-in irregular expression facilities. And surprisingly, these are actually not that fast, which we wouldn't have expected, since the built-in regular expression libraries are usually quite fast in these languages. Another interesting comparison is to compare Kleenex to more specialized tools. So this is an inherently deterministic transformation, which just projects a column from a CSV file. So compared to tools like cut, cut is very fast since that is specialized to exactly that task. General purpose languages like Awk and Perl and Python and also libraries like Uniguma, operate around the same, like half a gigabit per second, whereas Kleenex in the fastest configuration is it can process data faster than 2.5 gigabit per second. And the interesting takeaway from this is that if we compare this to a tool like Radial, which also is a tool for compiling finite state machines into C code, the performance is actually comparable. And since this was a mainly a deterministic program that didn't really benefit from this equation, the takeaway is just that it doesn't add any complexity on top of inherently deterministic tasks. Okay, so finally, I think I'm running out of time, and let me conclude. Future work that would be interesting to pursue would be to look into things like other disambiguation policies, for example, POSIX, or maybe changing to approximate matching and choosing the match with fewest mistakes, or probabilistic matching and choosing the one with the highest probability. There's still some engineering effort to look into different optimizations like multi-striding and parallel processing. And to make this more practical, it would be interesting to see if we can increase the expressivity in the path tree model by extending to something like visibly pushdown languages, to which would allow us to at least pass something like Lisp. Okay, and with this, I'll be happy to take questions. Yes, but it. Yes, but it's beneficial from an expressivity point of view to allow a context-free grammars, since some transducers at the machines that we operate on don't have a compact representation as regular expressions. So sometimes you will get very nasty blowups when you have to write that way. Yes, we have, but not in the general form that we see in these tools, because that is, as most of you probably know, that's going to incur a pretty bad worst-case cost. So we have thought about looking into various restrictions of that would fit nicely into the path tree model and not blow up that bad in the worst case.
Thank you very much.
Thanks.